The LMT is actually the intersection between the Taiwanese community, especially in ASIAA, and the North American community. For people from North America, I believe you know that you can apply for LMT observing time. And from recent years, astronomers in ASIAA started to become interested in this telescope. We think our experience in radio science and instrumentation can allow us to contribute a little bit to this project. So we started to talk to the LMT. So that's why we invited Professor Min Yun from UMass to come here to join this North American Taiwan workshop, and at the same time giving a talk about the LMT project. So Min is a professor at UMass Amherst, and he is also the UMass lead for the LMT project. He knows this project very well, and he had quite several meetings with us in the past months to discuss about how we can collaborate on this project. So I believe here he will talk about the synergy between LMT and ALMA. So both the astronomers here and the North American astronomers who are interested in this LMT project can learn a little bit about the Large Millimeter Telescope. So without further ado, let's welcome Min Yun.
Thank you, Weihao. Thank you, everybody. Just like you, I prepared a 30-minute talk. And then within the last couple of weeks, it's been elevated to, yeah, you can talk a little bit longer. So I'm very happy to talk about that. So I'm not going to change my talk too much because there are some things I'm very passionate about, I'm very curious about. I peppered this talk that sounds like it's going to be like a production talk about the project, but in fact, I'm going to talk more about science questions I'm interested in and problems I'd like to solve. So there's going to be a lot of that in the content. But if you have any general questions, feel free to ask. Since I have a little bit extra time, I'll start with a little bit of introduction about LMT. I think a lot of people in this room know about it, but there are some people who are joining the workshop who may not be completely familiar with some of the things or the current status of things. So I'll start with that conversation, and then I'm going to touch on a couple of things about ALMA and LMT that might be important in the long run. So here's an outline. There are just two separate topics I'm going to touch on in half an hour, I thought. But just to introduce the LMT to people, and the more I think about it and take my time, this really is a really challenging but remarkable facility. So it's a 50-meter diameter telescope. Now we have 100-meter, 500-meter telescopes in the world, so it doesn't seem like such a great thing. But just think about it, 50-meter is the Olympic swimming pool, right? We configure a telescope that big to an accuracy of a sheet of paper across the entire surface area to a perfect parabola. And we try to maintain it throughout those observations. And also, we steer that entire swimming pool at a speed fast enough to track a satellite across the sky, but come to a dead stop and point at your target within an arcsecond of where it is supposed to be. I think only radio astronomers did that. I think astronomers given up on this from the get-go. They figured out some other way to do it, and we're beginning to adopt this strategy as well. So there are some tall poles we set for ourselves, but we're actually pretty close to achieving that. At 3 millimeter, it's already a perfect instrument, perfect surface. We're right now trying to perfect the system at 1 millimeter. To accomplish that, there's a finite element model that we rely on, and there are a bunch of sensors that we will try to rely on, and there are some auxiliary hardware that we're trying to install to make all of these things happen at 1 millimeter. Of course, the surface should be accurate to about 70 micron. That means not only we have working instruments out to 1.1 millimeter, but we think we can get up to 350 gigahertz and have 4 arcsecond beams. This is a telescope designed by a German engineering firm in the mold of other major radio telescopes German engineering has accomplished. But that was 30 years ago. So one drawback is that the field of view, no one thought you're going to have big array cameras in millimeter wavelength 30 years ago. When ALMA was built, someone said, oh, we're going to need 1,000 SIS receivers. And at that time, at most, we built 100, and when you add up all the instruments we've ever built in the world. And there was some skepticism whether you could do it. So these people thought, well, okay, we'll never have to worry about that. But now our goal is to fill our focal plane with detectors, and that's one of the things where I want to go to, and this is one of the reasons why I'm going around the country, around the world, and trying to find people who are interested in that kind of new challenges. If you haven't did a Google map search of LMT, we're located about a 2-hour drive from Mexico City. So that means if I leave home 6 in the morning, that's when all my local flights will leave, I can be on the mountaintop that evening, except, of course, you shouldn't go from sea level to 5,000 meters in one day. But at least you can do it. We're much further south than Cuba, or even Cayman Islands. It's actually 19-degree latitude, which means same as Hawaii. So I guess a lot of people in this room are familiar with JCMT and how, what the sky coverage is like. It's very similar to that. And the altitude is, we're about 1,000 feet higher, but a lot of other things are very similar. And if you have the pleasure to get up to our mountaintop on a 4-wheel drive, you're gonna get that feeling of deja vu, just like going up to JCMT on Mauna Kea. It is very similar kind of feel, well above the tree line. This is a picture of the mountain we're on. Actually, there's the Pico de Arizona is the tallest mountain in Mexico. It's 5,740 meters. Our peak is this one, Volcan Cerro de Negra. If it were anywhere else in Mexico, this would be much better known. It's the 5th tallest mountain in Mexico. But when you're next to the tallest mountain in Mexico, no one really cares about that too much. Good for us, because they let us build something on top. That little dimple on top is our telescope. Okay? And it's a national park, so actually, somebody asked me whether I'm a ranger for a Mexican national park. We don't have a single one with a ranger outfit, but we are in the national park, so we may be running a visitor center soon. It's a beautiful place to go visit if you have a chance. The site, of course, is high altitude because you need high altitude site for some millimeter astronomy. And during the winter months, our site is about as good as ALMA site, I would say. And so this is 1 millimeter precipitated water at the first quartile, but usually half the time better than 2 millimeters. And during the winter time, site is wonderful. During the summertime, it's more like being in Arizona. If you've ever been in Arizona, you get afternoon thunderstorms. So we have that kind of weather, which is not great for astronomy during the daytime. But my colleague, David Hughes, who spent his career building things on Mauna Kea, insists that our transparency is really good throughout the year. And in fact, so much so that we should really push our capabilities to higher frequency windows, and we're all agreed on that. I'll just skip that. This is just a panel. Let me point out this podium is size of one of our panels on our telescope, and there are 180 of them. Okay, so it's enormous. It's just, unless you be there, you can't tell how big things are. And this entire structure, there are 8 segments, and they're aligned to about 25 micron accuracy. Oh, another ALMA synergy. The company that built ALMA antennas and their panels built our panels as well. So it's actually same material, same technology. And this entire frame is resting on this structure, which is actually connected to the actuators that will adjust in real time, so that we maintain that shape using finite element models. And that has worked pretty well. Actually, there are some statistics. We have a group of people who are doing this work from the get-go. It took us many years to build all the panels and align them all, but over time we got better and better. So now I think all the panels up there, we're gonna go through the cycle again and start taking down these panels and ship it down to sea level and have them fix it back up and bring it back on. We're a little bit late in getting the instruments in the modern standards. If you look at the list of these instruments, these are two 3mm instruments, 1mm instrument, these are 2mm instrument, and then Toltec. Toltec is absolutely modern, state-of-the-art, and that's an instrument we're very excited about. If you haven't heard of Toltec, I hope you don't exist, but it's a 7,000 pixel mega 3-color camera. It is absolutely a remarkable instrument. Very excited to design with that. Sequoia is a very old 3mm head-around camera, but it works beautifully. I can show some images from LMT. I mean, it's basically a new camera on a new telescope. But all other spectroscopic instruments we really need to update. So there's a plan to do some of that. So for example, ASIAA is a 4x2 element band 6 receiver that will have digital backends, and we'll be able to make images, spectral cubes of things that are relevant for today's discussion. There are some spectroscopic instruments that will cover all various ALMA events simultaneously. There's some desire to have ability to do the spectral scanning, but in one shot. For example, the RSR instrument can cover the entire 3mm window without any changing the tuning and simultaneously get that 38 gigahertz in one shot in two different pixels and two different polarization. But it uses some archaic kind of instruments that you only hear about in classroom, and we think we should really upgrade that to a digital backend. So today, let me start with, well, my talk's going to be focusing on two things. Just to explain the background a little bit, when I was a Jansky postdoc, this idea of ALMA became reality. So I joined, myself and Brian Butler, two Jansky postdocs in Socorro, joined Al Witten to be basically core of the ALMA calibration working group for NRAO. And I was very passionate about the imaging part. So I became the lead of the ALMA configuration study group for North America. So I see a lot of my DNAs in the ALMA configuration today, and we had some really good arguments going back and forth with groups in Europe and in Japan. Some kind of heated, a lot of hurt feelings at times, but in the end, I think ALMA has producing some really remarkable results because of those really hard work and late nights people pulled. So I feel a little bit of ownership, a little bit of pride. If you get really nice data, send me a nickel. When Aaron mentioned the Seychelles Tau image, I had a very different experience. Al Witten sent me the picture, 8 in the morning, when it was allowed to go public. I got up, looked at it, and go, oh, you sent me the wrong picture. Is this one of the test images we made? We're using numerical simulation picture and the test arrays. And he sent me an email right back and said, no, that's a real thing. In an exclamation mark, like, oh crap. This is really working like it was supposed to be. That was really great. As part of the designing team, I know where the strengths are, and I know where the weaknesses are. One of the real weaknesses of ALMA, as wonderful and powerful it is, it's not really a great instrument for imaging extended low surface brightness objects. And I'm going to deliver that message to very brutal fashion, and then explain how we might be able to do that better. And I think there will be some significant impact on some of your science cases if you can do that. And then the second part, of course, its field of view is not very large. If you have a hammer, every problem looks like a nail. So we try to come up with ways of addressing that issue by doing mosaic observations and whatnot. But in the end, it may not be the best way of doing the science you need. So I'm going to talk about how LMT might be very important for that. But just to go back to the first principle, just lay out the problem where they are. And I found this in Wolfram Demonstrations project. Basically, interferometer is high-pass filter, right? When you make an image, you have an idea, you have this beautiful object that you're going to make a very detailed picture of. It's really amazing concept. I'm only astronomer I know who decided to make career in astronomy because Fourier transform is such a beautiful technique. True statement. I thought that was it. Like, oh, now I know what I'm going to do. I'm going to build in the interferometer. Because that math is so cool. Okay, yeah, this is really what you get. And then you put a lot of your imagination and your scientific knowledge to derive scientific information from it. If you really wanted to recover brightness distribution, like what you really are thinking about, you really need a photometer. But then the photometer doesn't give you a picture, so you have to have a camera that will have an optics in front, that will have angular resolution, and even with a really big telescope, you get a picture like that. Of course, all along what you had in mind was something like that. Well, okay, I couldn't find the actual picture they started with. That's also another filtered image, but you get the message. You really need to combine both high-pass filtered image and low-pass filtered image to construct more image that is closer to the reality, if there is such a thing. So that's ALMA, that's LMT. Hopefully this is what you're going to get once you are able to put those information together. This is actually one of the lecture slides from my radio astronomy class. You can tell how dated that is from the president who was at power at that time. Although history has an amazing way of repeating itself. But I wanted to get students worked up a little bit. So, title is ALMA $1 billion fraud. But it's really addressing this question. What is the image you get out of an interferometer? We do a lot of work to start with a dirty image to get to what looks like a beautiful image of a galaxy or protoplanetary disk. And one of the things you don't really think about, probably you know but you want to in denial, is the fact that that image you produce is still a model. Model of what the information is contained in the data, but it may or may not be anything like reality. And this whole statement about the convolution equation is that it's a linear sum of term that looks like being convolved with some clean component or some such thing. And you can add infinite number of functions z that when you convolve with the beam that gives you 0, because then you're adding just 0 to it. It doesn't change a thing. So a very simple example of z is a constant value across the whole image. You may think that interferometer resolves it all out. And in mathematical concept, this is what it is. You convolve with the beam, which has no, essentially 0 area under the curve. You convolve with a constant, you get 0. So keep in mind, when you have really beautiful data from ALMA, you don't have to send me an email. Just remember that your image is a beautiful representation of the thing that you want to study, but it may have things that you don't see that you may need to be aware of. Okay, so this is another slide from my lecture, and Brown and Walter Brothers describe this in a way that many of us experience, the missing flux problem or the negative pole problem, right? So the way Walter Brothers basically explained, this is where the Fourier transform comes in, when you have a boxcar in spatial domain, if your Fourier transform counterpart is in angular space, appears as a sinc function. Okay, you've all seen that. Well, except in the real interferometer, you don't actually have data in the short spacing part, because if you put two telescopes together at their diameter distance, they run into each other, and you're going to be destroying these $1 million telescopes in an instant, and you will be kicked out of astronomy forever. So we don't do that, and the shadowing causes the data that's a closer interjection to be useless. So there will always be a hole in the middle. Well, Fourier transform of that is also a sinc function, except now it has much broader spatial angular response. So what you end up with is more like a bun cake, that you have a flat top thing but middle cut out. And in the Fourier transform space, and then for the PSF, basically you have this PSF, but you have to subtract it, so you have a deeper hole underneath. Okay, so this is a very beautiful illustration. Exactly as how this translates into negative features in your map, that's a lot more complicated. There's no easy way of describing it other than, I'll show later what sort of the distribution, the baselines and the weights look like. What you see is that on the very short end, the shortest baselines you have, there are only few measurements that can tell you that there's a lot more flux in the inside of that innermost baselines, but you don't have enough samples to make any kind of image out of it. And all the flux it sees, your Fourier transform wants to put it somewhere, but it doesn't know where. So it'll put it somewhere where it thinks it is, but all you're going to see is that the negative response, this part, because it doesn't really know where it is. Actually, I have a really beautiful example of this, and it kind of stumped me first time because it kind of broke everything I thought I understood about interferometry, and took a while to figure out this is what happens. And just to describe the problem, this is an image of cosmos field taken at 1.4 gigahertz in B configuration after 1,000 hours of observation, and Jen's giving us that annoying smile. Amazingly, well, we can get continuum as essentially at the same time, right? So this is a continuum image for the H1 cosmology project. And after the first year of observation, 108 hours, 80 hours, we got this beautiful image. Oh, this is really exciting. It's like I've never seen a radio sky lit up with sources like this. It's very exciting at 5 arc seconds. And then the year after, we had double the time, made a map that looked exactly like it. It's like, who screwed up? There's a running theme here. After 1,000 hours, image looks exactly the same. What's happening is we've reached the confusion limit, so that what looks like a noise in the background is in fact essentially a forest of radio sources in the sky. So it's really not noise. Now, the way you characterize these really faint sources is then to model this distribution of pixel values and make an assumption about their number counts. And then you can actually reproduce and make inferences about the faint sources. Jim Condon always said this is the really way to figure out what the micro-Jansky radio sources are. So here's a histogram of the pixel values. I was trying to repeat Jim Condon does here. Whatever Jim Condon does, if you can repeat, that's pretty good. So here's the red histogram is the pixel value. And it's almost Gaussian-like, but on the positive side, it's a little bit higher than 0. Those are the really faint sources that you may not see individually, although when you go about 10 microjanskis, then you can see them individually. So some of these sources, that source probably is like 15 microjanskis. I just picked the number. Normally, in an image like this, you would think this is a Gaussian noise. Well, we know after 1,000 hours, we should have thermal noise of about half a microjansky. Full width half max of this thing is like 1.5 microjanskis. And it was always there after 180 hours. So we know part of it has to do with sort of the dumb standard Fourier transform we do to make images. This conferences about wideband spectroscopy. When you have a wideband system, there are a lot of systematic things that do not work like you do you learn in your classroom. All of the classroom calculations for monochromatic light, once you have a significant bandwidth, you have to worry about a bunch of things. So please keep that in mind. The thing that really surprised me is that when we looked at the peak, that peak was not at 0. The peak was in the negative value. And I sent the student back and said, analyze it again, you must put in some constant in there or something. But no, it really is a negative. And I thought, how could it be? And then I stare at the image and go, it does look a little bit negative. So it turns out there's about half a microjansky of floor, negative floor in this image. Never heard of that before. I heard of negative bulb, but there are no bright sources in here. It turns out the Meerkat team had made image this deep a couple of years ahead of us. And they actually talked about finding this bulb. Without any explanation, they said, there must be some offset that is shaped like a primary beam, they're going to subtract it. And we thought, I'm curious why they did that. There wasn't any explanation, but when our team talked about this, so this is sort of our estimate of what the shape is like. It's not constant, it is bowl-shaped, but it's not the shape of the primary beam either. So what we surmised is that we cleaned this map to about 3 sigma in this RMS, but in fact, we were cleaning down to like 5 sigma sources for individual objects. So that means we stopped cleaning at 5 sigma. Probably some of you have done that with your imaging. There's going to be artifacts you didn't clean deep enough, right? Basically, what we think we see is that there are numerous sources in this field that we didn't clean. And their collected negative side lobes are piling up. And this flat point is our model of what are those uncleaned sources below the clean limit. Convolve it with the PSF, and we just randomly threw down what we understood to be undetected or confused source population. And that's the shape. So we didn't quite match it, but then this analysis assumed it was thermal noise, so we probably did not guess the underlying population very well. There's a group at NRAO who actually are using full W-term imaging. There are a bunch of other things you have to do for wideband data, and they're doing that, and they're reporting smaller noise. I don't know exactly what they are because I haven't seen them. I haven't shown you their data, but they say it's much better than your data. Well, we'll see how that goes. But this was really interesting work. So there's a paper by Nick Kluver, if you want to read a little bit more about it. Also, Han-Sang Kim wrote a catalog paper on that, and there he talks about the importance of this impact of this wideband data. The fact the bandwidth of the data that we're using for this imaging is about 40% of the frequency. So it's a very big chunk. I don't know if we will, you may not need to worry about that for ALMA, but you may begin to think about some of these issues when we get there. So that was really interesting. Negative volt from a bunch of below noise objects that we didn't clean, and they have a real impact. Okay, let's get back to the program, actual problem of negative vol and how to deal with it. So this is actually an instrumentation paper written by the ASIAA team in Japan, describing what the problem is. The 12-meter antenna alone, there's going to be a hole. This is essentially a density of visibilities below 12-meter diameter. I'm not quite sure what that part is, but okay, maybe they included some sort of shadow data. And of course, this is exactly the problem of bunking I started with. If you don't fill this hole, you're going to have accentuated negative hole that you're going to have to deal with. So actually, during the initial stages of configuration design, we discussed how to solve this problem. traditional answer and executed in some of the instruments in Canada is to build a big single-dish telescope that's twice the diameter, so that if you have this is a 12-meter total power array footprint. Not surprisingly, I think of a big single-dish telescope as a small analog interferometer, an autocorrelation interferometer. So this is like interferometer version of a single dish for 12 meters. That's what it looks like. If you have a 24, 25 meters, it's going to look something like that, filling most of the space, but there'll be some gap in the middle. Obviously, no one wanted to have that gap in the middle, so then the idea was, let's build a smaller array that can fill this gap, and that's how this ASIAA came about. And here's the demonstration of what ASIAA does. It fills some of the gap, but again, short words of 7 meters, it's going to have a gap. So the idea was if we put in a 12 meter single dish, we can fill that gap. But if no one wanted to spend a lot of money on the additional 12 meter just to do this, so you end up with 4. So that means it does something, but perhaps does it do enough? So this part of the talk is really demonstrating that, and can we do better? So this is actually science verification data just to ask that question. So in 2011, they've taken 47 pointing of this CO emission in M100. And then a year later, they did the 23 pointing mosaic with ASIAA. And then yet another year later, they did the total power single-dish measurement from the 14 meter. And the image on the right is combining 12 meter and the 7 meter data together to make a CO map. And the image on the left is 12 meter plus 7 meter plus total power array. You see the difference? Well, okay, if you're not, you're used to looking at that. It's like, okay, here's a 12 meter single dish beam. That means it's gonna put in these big, broad, faint things in here, so elevate some parts. So this part is a little bit higher than that part. But largely, you don't see huge difference. That's because you're missing spatial information on that intermediate scale. Okay? Okay, the problem's a little more complicated than that. But Il-Sung Yoon, who was actually a theorist at UMass, but now he lives in interferometry because I got him to work on Toltec, Toltec predecessor Aztec instrument. He said, why don't we use LMT, make a total power map, and see how effective that was? So we basically asked for enough time to match the surface brightness sensitivity at sort of that LMT beam, 12 arc second beam. It required about 8 hours of observation. So we went ahead, got the time. Here's our web log version of what the data is doing. So Sequoia has 16 beams, 2 of the beams kind of crapped out, so they got flagged. Then everything else just added up together. I think it was like 38 or 39 individual scans. And this is a 3-dimensional cube projected. This is a fancy thing our colleagues at the University of Maryland is doing. So you can see that, oh yeah, it's pretty well detected. CO emissions there. Perhaps a little bit low resolution for ALMA aficionados. Now we have to combine the data together. Well, it turns out that's not so obvious either. There are a few tools in CASA, but as you know, just because there's a script in CASA does not mean it's going to work and give you the answer you want. So yeah. Feathering is basically make Fourier transform images of 2 different sets and then basically weave the data set together where they overlap. It's been used for a long time, and a lot of the millimeter data sets that are combining interferometer and single dish actually use this technique. If you imagine, you should do the same with the PSF so that you can have an effective PSF that's feathered. Imagine feathering 2 PSFs together like that, and it's going to be ugly. In fact, whenever you combine 2 configurations together, that beam's not going to be looking anything like a Gaussian. So you really should be worried. A VLA multi-configuration mosaic is really hideous. Always check your PSF. there's what we use is SDint. So there's a CASA function that does feathering. There's also a CASA function that's SDint. We tried both, and there was no question that the feathering is not doing what we wanted to do, but we didn't really play around with it too much. Oh, by the way, Adele Plunkett, who is in this meeting, is an expert because she wrote the paper, the review paper. I recommend it. It really lays out the detail, and I really appreciate it. And honestly, I don't know what these two other things are, and we didn't bother looking at them. TP2VS is what I thought we would do, which is turn the single dish data into effective visibility. And then when you have visibilities, at least I know what I'm going to do with it. But there are only Gene Coda at Stony Brook seems to have the software at the moment. So we gave Gene all the data, and he's going to combine the data and give it to us, and we'll compare the nuts. So we're going to use this SDint, which is something you can do if you have the data and you're running CASA. So here's this is why we decided feathering wasn't going to be the way to do it. So the left side again, 12 meter and 7 meter data, 12 meter, 7 meter, and total power data feathered in. Didn't do much. This is 12 meter, 7 meter, and LMT data feathered together. I haven't shown you 12 meter LMT data. It looks exactly like that. Okay. So of course, you do Fourier transform and mush together. You're going to get what it looks like an LMT thing with some higher resolution bits on top. So very disappointing. Took milliseconds to decide this is not the way to go. I mean, to the credit to people who do feathering and develop the technique, there are a lot of knobs you can turn here. It's not just a one way to do this. So if we were really inclined to do this as our main way, I'm sure we could have done a little bit better turning some of the knobs, giving different weights and whatnot, choosing different ranges for feathering, for example. But we decided this is not what we had in mind. We did not spend all that effort to produce something that looked this ugly. So here's a channel map, because I don't think those integrated maps do the justice. So you're going to see a movie of running through the channel maps, and I'm sure most of you have done that, and you're very familiar with what you're looking at. I'll save you the trouble. The one on the left is with LMT data, one on the right is with just total power array. Okay. There you go. It's a beautiful data. It's a spiral galaxy. So you see the disk in differential rotation, and you see some significant differences in some channels. But to me, actually, it's not the difference in the emission that catches my eyes. If you look on the right, you can see these blotchy things that are surrounding the emission peaks. Those are the infamous negative bulk effect, right? Even though this has the total power data from the ALMA. And overall, you see more blotchiness here. I think it's just simply missing spatial components in this model image. And there are places where there's more emission. So this is an integrated map. Again, you may not say they're very different. Certainly in the middle, near the nuclear region, there's a significant difference. We recover about 30% more flux here. But if you care about the details, look at the blotchiness of the regions around the spiral arms. Well, it's much smoother in this area because you don't actually suffer from that negative bulk. So not only we recover more flux, which is important for some science cases, we also get rid of a lot of imaging artifacts coming from this negative bulk. So I was very happy with it. And again, we didn't spend a lot of time there. Actually, we're still working on some improvements. Once we decide to do this, we have essentially an arc-second resolution image, but there's like a couple arc-second offset between the single dish and the interferometer, because single dish can point to accuracy of the interferometer. And a lot of people ignore it, but we thought, why don't we align them? Even in a 20-minute observation, we could actually see the offset, and we could actually compute that through cross correlation. So preparing this talk got me to talk to my colleagues about, hey, we're going to fix this. So we're actually actively fixing that right now. We're checking the calibration so that they're on the same scale. We are playing with some of the knobs, so it's going to be even nicer, hopefully. And when you overlay this data, the combined data with LMT, on top of this Spectra 3.6 micron, which has stellar light, and then 3.3 micron pH emission, which probably some of these extended emissions are sensitive to, they seem to actually correspond to each other quite well. So I'm pretty pleased with this result. When I showed this picture to some people, they thought, well, is that, it's like that HL tab. Did we really tune their problem to that particular galaxy? So we pulled some other, specifically the question was, could you have done this with the 30 meter? And the answer is yes, you could. So here's a direct comparison of the same galaxy in 628 with the 30 meter on the left, LMT on the right. LMT is a bit bigger, 1.7 times bigger in diameter, so the resolution is a bit better, and you can tell in the nucleus the details are a little sharper here. But of course, the real difference is that this map took 18 hours on ERM. This map took 4 hours, about 20% of the time, actually. It's not just that object, this is M51 data, since everybody has M51 data. I don't know where Mark Haya found 45 meter data, but there it is. He convolved the LMT data to 16 arcsecond resolution because he was not interested in CO, but he was interested in HCN emission, that you can observe it simultaneously. And his conclusions are quite interesting if you're interested in dense gas mass fractions. So I'm quite pleased with that exercise. LMT at 3 millimeter works exactly how we promised. And it's going to do a really nice job. Several people mentioned combining total power array data to recover extended fluxes. Maybe you should think about using LMT and see how much better maybe you'll be able to do. The next part is, because everybody wants to know what Toltec's doing, I want to introduce sort of the Toltec progress and what we learned. But in the context of, you might want to have a big camera on a fixed English telescope if you're interested in extended emission. So this is just showing that the Toltec is made out of 3 different bands with 7,700 dual polarization kits. It's polarimeter. I didn't know that until I actually built it, but I'm glad we did, because now we can measure magnetic fields. There are so many detectors. We don't pay attention to single individual ones, but we want to make sure statistically they are working as we promised, and they do. There's some distribution of sensitivities, but they're all within this fact. These are full half max of all the beams. There are 7,700 beams, and we have to measure and analyze statistically. It's actually more or less to this fact, about 5 arc seconds for 1.1 millimeter array, around 10 arc seconds for 2 millimeter array. But there's a difference at the moment between the azimuth direction and elevation direction. We think there may be some issues with the collimation, but I don't think you're going to notice that in your map, but we'll make sure it is reliable. This is how it is installed. All of these are supporting equipment. This thing that looks like a shiny coffin is the actual camera. And NSF gave us $7 million to build this thing. What we promised NSF is that for that, we'll do some legacy surveys, give the data to the community so that everybody can do science with it. So there are 4 legacy surveys that are designed by a couple hundred people who visited Amherst in 2018, November, just before COVID hit and we had to shut down. We defined 4 of these projects, and there's so in case you're not familiar, 2 projects are elective projects, trying to understand the structures of GMCs, and there's another project that is taking advantage of the polarimetry. At this meeting, it seems that half the people are interested in the magnetic field. I've never seen so many people are interested in the magnetic field. So I'm very excited that we will be able to do this and connect this Planck scale down to a really ALMA scale at between 5 and 10 arcsecond resolution. And I mean, call out Sarah there, but there are many people who talked about magnetic fields at different scales, structures at different scales, and connecting ALMA with a large scale phenomenon, structures, physical properties, whatnot. I think that's going to be actually pretty important if you want to understand this whole thing. Oh, please don't take a picture of that because it's not my data.
No, I was about to take a picture of the previous slide. I missed that. Sorry.
Excellent. You can go to our website. There's a whole website on this, and you can join the project. This is actually this is another one of those weblogs of our pipeline. But I was so pleased with this beautiful image of what's meant to be like a square degree CO, 12 CO and 13 CO map of G45. I'm sure somebody knows what that is. But in 12 CO, you're using temperature distribution. In 13 CO, you're seeing column density, and you see filamentary structures everywhere. So of course, some of these things are going to be related to magnetic activity. Some of these things are going to be related to the collapse that you're going to trace with high resolution with ALMA. And of course, everything is connected together, and understanding the environment will be, of course, quite important. I mean, for me, I try to do that with galaxies, so I'm sure it is true for star formation as well. Nakamura-san showed an image of this thing earlier. You had my full attention, because I didn't know what this was before. So, this is a Herschel column density map from the Herschel bands. This is a 40-minute integration in all three colors. This is a color image of the same object with Toltec. And there are point sources that are popping up that we didn't see before. And that is long filamentary things that we didn't see before that shows up. So I don't know nothing about these things, but if you ask me, something like this probably is associated with magnetic field. So Joey Golek, who has actually studied clusters of galaxies, and CMB, he just turned on, make a polarization map. Again, I looked at Nakamura-san's polarization vectors and go, kind of close. This is why there's a big preliminary thing, like a bunch of amateurs made that map, so don't trust anything, just take it as a qualitative exercise. We should be able to do it. And in fact, we are also impressed with this feature. We should integrate a little bit deeper and see if we can have a sense of polarization there. So there are about 15 projects like this. They're all limited to the Band 1 demonstration project. We're not allowed to do anything any PI wants to do. Hopefully something dumb and boring, or boring enough that you can demonstrate capabilities and test pipeline, test observing modes. That's what we're really trying to do right now. We're almost ready to start science operation, so we will be talking about that probably in the coming weeks. Here's another project that I want to mention, better hurry up. So this is a Fermi bubble in the Milky Way. The idea was that in 21 centimeter H1 line, they found these clouds, H1 clouds, kept entrained inside the Fermi bubble. And the idea was, is this an entrained material, or is there molecular gases forming within this outflow in the context of feedback? And it turns out only one of the two objects had CO emission in it, and these are clumps that are not bound, that their virial ratios are bigger than 100. So it seems they're ephemeral features that are showing up within this cloud. Whether they're forming or disappearing, I'm not really sure, but they're non-stable clouds. Okay, so there's some obvious things you can draw from these exercises. There's extragalactic projects, but I think I'm going to just skip it because for the benefit of time, just to say that I'm studying these lens objects that are very, very bright. It takes minutes to observe, and we're using ALMA to image them at tens of milliarc seconds and pressing lens modeling people to produce images like this at millisecond resolution with ALMA. How do you do it? Put a big galaxy in front of it. Spiral galaxy at redshift 2.5, forming stars at 3,000 solar mass per year. I don't know how you do it. That's why I studied them. No clue. But we're collecting some very interesting data. Another interesting set of objects we find are like this. There are 18 CO-emitting galaxies in this particular direction. There are a lot of talks about protoclusters. Now, how do you form objects that big? You have to start with overdensity. And you're going to build big galaxies in those areas. And maybe these sub-millimeter galaxies we see, and also these universe breaker, massive, passive galaxies we find at these redshifts must be signposts of these overdensities. So that's all good, but the question, oh, that's a movie. All right, I'll show the movie once. There are people who are simulating what those protoclusters would look like, and I want you to just watch the scales. It's not a very long movie, so I want you to just watch the scales. Maybe not. Oh well. All right, no movies today.
2 slides ahead.
2 slides ahead. Do you really want to see the movie?
I mean, if you want to show it, I'm just...
Okay, yes. Let's watch the movie once. All right, so that's 100 kiloparsecs at redshift 20. Okay, don't see much, but when you, I don't think it's going to play. Okay, so there are objects that are like 10 megaparsec size. You think it's going to collapse into something massive, it's going to have to start with something bigger, right? Well, except we can find these things only if you do spectroscopic redshift surveys in the cosmos. It's the only one we know about. There are a bunch of things that the ALMA folks have found and claim to be protoclusters, but ALMA field of view is so small, these things are over a couple hundred kiloparsecs. And cut to the chase, this is one of the picture frames from this movie of a protocluster, a snapshot at redshift 5.5, and these are individual band 1 field of view for ALMA. So I'm not sure what you can really learn from one of the single pointings. This is more like what I think you're going to learn from it, and people will be arguing what it is they're looking at and why they don't agree or don't agree. I really want to talk a little bit of time talking about this because it's a graduate student work. So what we have here is one of those overdensities magnified by a foreground cluster. And these 18 objects are at exactly the same redshift in tall CO. Some of these are all of them are dust continuum sources. Altogether, there's about 10,000 solar mass per year of circumvention happening here, over about 300 kiloparsecs area. So Nick is studying this as an example of protocluster. He actually studied by modeling this lensing. This is his JWST picture, pretty spectacular. Every one of these things are in fact lensed through this particular cluster. And there are some really red objects in this picture that we have not detected. Not sure whether they're at different redshifts or they're simply not CO emitting objects. I don't know how you coordinate. There are 11 individual galaxies that are emitting CO. I don't know how you coordinate 11 galaxies to undergo star bursts all at the same time when they only last probably 100 million years. So there are lots of good puzzles in this problem. I invite you to think about that. And it turns out that is just this part. And when, of course, looking at the movie like that, you wonder, is that really the whole picture? So Nick put together spitzer images. We found this structure with red galaxies spreading much further to the right. So he actually is a PI of a TOTER project to look at this thing and image 8x8 field, including all of these, and see if we see overdensities in some millimeter. And to prepare to study and prepare for this talk, I thought, could we have done this with Sequoia on LMT? So I did a quick calculation using our sensitivity calculator. We can map this whole region to the massive CO luminosity sensitivity of our LMT ALMA project. at 15 arc second resolution in about 8 hours. I'm going to write that proposal and then go back to the tech and say, all right, let's try this one. See if we can find the same objects with the top. So this is really my last slide. Of course, another very important synergy is for EHD, where LMT is over there, ALMA is over here. The two largest collecting areas in the whole configuration per baseline sensitivity is square root of the two pairs of antennas. So ALMA and LMT basically lifts the sensitivities of all of the small antennas in EHD. So for EHD project, they really like hundreds of hours ALMA time, like what we all do, but they also want hundreds of hours ALMA time, and we might be able to do that. Okay, that's really the talk today. I know it ran a little bit longer because I got excited about telling you some stories, but I'm glad you indulged me. Thank you very much.
Questions?
For the ultra-deep field survey that you showed, what are the confusion limits, like in terms of comparison with Herschel or
You were interested in?
sorry?
What was your interest?
I'm talking about the ultra-deep field
Yes.
survey, and what are the confusion limits in
Oh,
comparison
we
to
expect the
Herschel?
confusion limit to be about 25 microjanskis. So a lot of the surveys of similar galaxies of ALMA go down to about sigma of 100. So it's going to be deeper than ALMA, typical ALMA surveys. And in fact, we are going to detect the sensitivity, 5 sigma sensitivity, I think, is 10 solomons per year. And L-star galaxy at that redshift is about 30 solomons per year. So lots and lots and lots of galaxies we're going to detect will be part of this new way everybody's doing galaxy evolution. Big sample, lots of data, and then shove it into some machine that grinds through and chews on data sets.
And for
Because the resolution is much higher, so I believe the confusion limit must be much deeper than Herschel.
Yeah, that's right.
That's really interesting, yeah. And in terms of particularly the protocluster course or the protoclusters, like over the larger field of view, so you have the images you showed, were they ALMA plus LMT, or was it just LMT?
What I showed is just ALMA. We don't have the LMT data yet.
Yeah.
It's in the queue.
Okay. Yeah, it would be really interesting in terms of the diffuse structures. Yeah.
Same here. I'm dying to see that image.
We have a question here first.
Thank you for a nice talk. I was just curious that if LMT will help like a lot of extended structure, is it going to be a hope to have like LMT ALMA joint proposal? Because I think it will be hard for the community to just like, have the data for ALMA and then just like, oh yeah, we need LMT. So is it any plan or any vision?
I think
Yes.
I've been doing this long enough to know if there's a need in the community. I'm speaking for NRAO, so indulge me. NRAO is always willing to work with the community and what the community wants to do. So I suspect if there's a need, there will be a path. At the moment, there's not even a discussion. I'm 100% sure Phil wasn't even thinking I was going to ask that question.
Thank you, Min, for that talk. Sorry if I missed this, but how's it going to work? Is it open skies, or what is the amount of time that at least the North American or Taiwanese people are going to have?
I don't think anybody else knows yet. That's going to be part of the discussion. So at the moment, it's 70% Mexico, 30% US, UMass. We give away half of the UMass time to US community because NSF is giving us time, but we don't actually check the membership of the authors at the moment. And we're trying to maintain that. That's really the point we made to NSF, why NSF should continue to support the user community of the LMT.
In the Mexican part, they haven't determined anything yet, how the time is going to be distributed?
I don't tell them how to do their thing, and I try to stay out of it. We make a joint decisions, but totally respect their independence.
Thank you.
Yeah. So I want to ask about the surface using actuator surface correction. Is that real time or based on the model?
We've been using lookup tables and finite element model. We're in the middle of changing that right now. Because Toltec's operating, we're actually using, we can make PSF of Toltec in about 3 minutes. And we do this in 3 different focus positions. And then we can solve for Zernike polynomials we need to correct the surface. It's just that the search algorithm has not been as good as we had thought. It's very complex optimization problem. So latest attempt is turn on AI, the magic. See if the magic will save us. No, we don't really trust that, but at least throw all the problems at it. That's really the active research we're doing right now. There are reasons why we're not doing astronomy observations during the cube, because we want to give the best data possible, not excuses why it's not as good as we thought it would be. So we really had the goals to start doing PI projects this spring, but that particular problem I just described, it's a lot harder than we thought. So we're having a meeting twice a week just on that topic.
Okay, great, thank you.
Yeah, I'm curious as to how the, okay. I was curious about the public release data. Like, how will that be done? Like, I assume there's no archive.
There is archive.
There is an archive. Okay.
And your NSF had paid for it. So we actually have archive ready to go. All the data that we're taking with RSR, Sequoia, and Toltec will actually go on archive. And you can do, we're completely modeled after ALMA archive. So it's going to look and feel like the ALMA archive. I'm not going to have as much data, I'm sorry. It's going to take time to fill that archive, but we will, and Toltec's going to build the thing like super fast. But it's going to look and feel exactly the same. You can download the tar files. We have some plans to teach people how to look at data cubes and things. So for you, it'll be a piece of cake. For other people, it may take a little getting used to. But that's the goal. It's from end to end. We execute the project, do the QA pipeline reduction, do the QA processing. So some of the plots I showed were actually talk for the QA processing and archive. So you don't have to worry about running these big data files.
So would you show the slide or plot done by the Iguchi-san, the Japanese?
All right, nobody point your cameras at it. I'm gonna be in so much trouble if someone shows this somewhere else.
So my question is that basically, if I look at that plot, then the current total power array is not actually reach the design goal, right? And then you actually show comparison between 2 cases. One is with LMT, and the other one is actually total power array.
Right.
And then there are quite significant difference in the central part of the galaxies. So here, can you say some technical information, like a missing flux, for example, and some fidelity of the image or?
Okay, we recovered 30% more to 100% of the single digit flux. So that I can tell you. Fidelities, there are metrics that we can think about. We haven't done that yet. So if someone's serious about getting LMT time to get the short spacing, we're gonna have to do that homework and characterize it.
So
the time is split 70% Mexico, 30% US, UMass. Is there any chance in the future that for other countries to become, buy-in or have some percentage of the time with LMT?
Absolutely. Mexican government is very excited that we're part of the Event Horizon Telescope. They don't seem to know that it does anything else. So they are wondering, why do we pay in support 70% of the time? We'll continue to fund you under the condition that you find more partners. Well, that's part of the reason I'm here. I represent the LMT project, not UMass in this particular case. And we're talking to a group of other people who might be interested in having access. We haven't talked to everybody yet. I want to start with friends. We're not very desperate, but we are certainly open to having partners. So if you have some cushion change that you want to spare on telescope time, well, let me know. I actually know you, so.
Yeah, so you mentioned, you showed the beautiful cubes with M100, right? Where you say that the negative balls are, well, you said that you still have negative balls in the ALMA plus 7 meter plus TP. And I did see some negative balls in the one that you produced with the LMT.
You did?
Yes.
Good eyes. Okay.
Especially around the nucleus. I think that was the main part. So where is that coming? Well, I know you also said that there are additional things to do. So is that hopefully the additional things are going to solve that negative balls that you saw?
That's the hope. It's a research project, as you know. I will be conveying that information to Ilsan and make sure he pays attention to it.
I'll talk to Ilsan.
Oh, you talk to him.
Talking about negative balls, even from single dish maps, for example, Scuba 2, I saw that all the time. So even single dish can be a high pass filter, like
it is actually the dirty laundry. Yes, that's another reason why we haven't. I mean, our atmospheric removal algorithm is light years away, much better than S6 days, but it's still not perfect. So there may be some artifacts coming from that. The Sequoia data does not have atmospheric removal problem, but we still do baseline fitting. So there may be some source where some of that imaging artifact may come from that. We'll have to look into it.
I love the idea of using large single-dish telescopes for improving zero spacing. I've tried to do this with instruments that were not designed for it. It is very hard, and this may actually be more of a question for Adele. But you showed combining LMT data in molecular line emission, but for continuum, you don't have the same receivers like you do with the total power ASIAA and the 12 meter. Have you given thoughts to how the different filter functions between LMT for continuum will be able to be combined with the interferometry, or is that something that is, a future problem for other people to think about once proposals start trying to do that?
I wouldn't say it's a future problem for other people. Okay. I mean, it's our data, so we should, again, if people are interested in that problem, we're aware of the issues. We publish filter functions for all of our detectors, but there are other complexities.
Yes.
In fact, one of the reasons why we're having trouble with it, what we call out-of-focus holography, is in fact that the model was written for monochrome light response, but in fact when you fold in induced electric field with a very broad bandwidth, it has a significant impact. So we're actually, that's the flavor of the week, problem of the week that we're trying to attack. So there are some subtle but important technical details one has to work out to make that happen.
All right, thank you, appreciate it.
Right, looks like we don't have more questions. Let's thank Min again.